by Adam Boulton, a security developer and senior security consultant at Corsair. A little background on Adam. He worked in IT since 2004 and has been programming since 2001. He graduated from Sheffield Hallam University with a first-class business. What was this?
Want me to do the introduction?
Sure, go ahead. Go ahead.
Okay, good afternoon, guys. I'll come on to my profile shortly. So how many publicly known exploits are there for Java RMI? I'll tell you there's 0 that have actually been published, which is kind of strange.
Use the microphone. Yeah, and we are recording, so you have to kind of not wander.
Okay, you can hear me now at the back? Yeah?
Maybe just take it off of there and walk away.
Is that okay now? I'll just speak really loud then, okay? So there's no publicly known exploits for Java RMI, which is kind of really strange because Java RMI is not a new kind of technology kind of service. It's been around for kind of 6-7 years, and I've been looking at it for around 2 months now, and I found at least 4 exploits that I'm going to be releasing kind of the advisories for in the following weeks. But today I'm going to kind of show you how to attack an RMI service. This is going to be a kind of new tool which I'm going to go over today. But before we get into all the technical detail, I'll just go over my profile. So I work for a UK-based security company called Corsair. I'm hired as a principal security consultant and research developer, and my roles range from anything from web application security assessments to reverse engineering, C++ code assessments, and developing some in-house tools, and I'm going to demonstrate one to you today. And before Corsair, I worked for the antivirus company Sophos as a virus analyst, where I would reverse engineer malware, understand its behavior and its characteristics, produce disinfection and reliable detection for the engine, and some of you have no doubt read some of the Sophos reports about malware. So it was kind of doing it on a day-to-day basis. That's where I got a lot of my core reverse engineering skills from. And then before Sophos, I worked for the UK government, the Ministry of Defence, where I got my security clearance. So this allows me to do UK government work. And in terms of more formal background, I graduated with a software engineering degree, and since then I've become a certified secure code assessor. And some of you may know about the Owasp Java Gotchas page, which I recommend you should check out. I'm a big Java fan, I love Java development and all the technologies. Now the Owasp Java Gotchas page is all about kind of little things you wouldn't expect in Java, some things that happen at the lower kind of API level. So I've been going through the API and discussing about some kind of things that are going to catch developers out and things you want to look for during a web application security assessment. So today we're going to look at remote method identification. So before I start with that, how many people have actually heard of Java RMI before? Excellent. How many people have actually developed RMI services? Excellent, okay. And who is actually running RMI services in their company or have any live RMI services on the net or internally? We've got a couple, okay. Okay, so we're going to talk about RMI and kind of what it is. I'm going to be discussing the RMI architecture, going through all the different layers. I'm going to be looking at where the flaws actually lie within the RMI architecture, and unfortunately it's not actually the developer level so much, it's actually its Sun's implementation. So when you start developing your RMI application, it's already flawed from day one. It's a great start. Then we're going to look at attacking an RMI service with RMI Spy, which is the new suite of tools I've developed, which Corsair use internally when we're actually performing RMI assessments. Okay. So I'm going to set up an RMI service today, and we're going to actually run through a full security assessment. And then most importantly, we're going to look at how to secure your RMI services. So what is remote method identification? It's Sun's answer to distributed computing. It's all about hosting remote objects and talking on an object level. Like I said, it's not a new service brought to you by Sun. It's been around 6 or 7 years. So many of you who have developed are going to be familiar with the Java RMI package, which is where all the API and all the kind of functionality you need to set up your RMI service. And if you're not familiar with kind of distributed computing, there's a few kind of technologies you can think of that you may be familiar with, like Microsoft.NET Remoting, RPC, DCOM, Corba. And if you're still not familiar with them, just think web services, this idea that there's kind of logic hosted on a remote server and you interact with it as if it existed locally. So in particular with RMI, it's about communicating between two JVMs. So you get this idea that only kind of one JVM exists. All the interaction happens over a network transparently. And the functionality you develop is all at the object level. So you develop your business logic layer and you host it remotely, and all the clients interact with it as if the object existed locally. And RMI is able to do this by using its own proprietary protocol, using object serialization, writing objects to the wire and reading them back off. And RMI is, I think, is a fantastic kind of service, extremely transparent. You don't need to become involved with any socket connections, reading bytes off the wire. So Sun really kind of went out to develop a service that was reliable, that work that was easy to set up. This is what they stated in their specification, and I think they did a fantastic job with it. And for those of you who have developed RMI applications, you know it can be a little tricky to get started, but once you've implemented the service, it works really well and it's kind of really seamless. But this does introduce a kind of security risk. When you read a lot of RMI or when people are taught about RMI services, it normally starts off with you have your server object and your client object, and then the rest is kind of magic, how it actually communicates. Well, guys, it's not magic, and there's actually a lot of security vulnerabilities that exist in these lower layers. So unfortunately, it gives the developer a sense of this security through obscurity. No one knows what happens at lower layers, because you don't have to become involved in it as a developer to kind of meet your deadlines to finish your development project. So let's take a look at the RMI architecture. I'm going to identify where some of the flaws are. So as a developer, you would put together your business logic. This is your server object. And this is where you yourself would actually use the Java RMI packages and develop your business logic layer. And then you have what's called the skeleton. And this is actually generated to you by Sun in version 1.1 of RMI. Version 1.2 don't actually need the skeleton. But we're going to concentrate on 1.1 today as the concepts don't differ too much. So at the skeleton layer, this is where developers don't need to become involved. This is all generated. And this is about marshalling and unmarshalling all your calls and your data. So this is kind of where some of this apparent magic happens. It's going to do all the kind of reading off the network, reading all your objects, writing them, understanding all the calls that are passed from the client. Then we have a remote reference layer. And this is essentially just the semantics for the invocation. It understands about the data types you're passing. You're going to be going kind of backwards and forwards and passing critical data such as the unique IDs, because this is how RMI communicates. Don't think communicates in the same way as web services. We actually need to know the method names. You actually need to use keys, and we're going to look at that in more detail shortly. And then obviously you're going to have your transport layer. RMI communicates over TCP/IP. And on top of that sits Sun's proprietary stream-based connection, the Java Remote Method Protocol. Not too interested in that today. And we've obviously got to have the transport layer on the client side. We're going to have the remote reference again, which is all semantics for the invocation. And then there's a slight difference here. This is the stub. And again, this does the marshalling and unmarshalling of all the calls where you would actually do your development from, where your client object is going to communicate through the stub, and the stub's going to take care of communicating to the rest of the layers to get to your server object. And the stub needs to be passed around by the developers or by the administrator. It needs to be available to you to actually use the RMI service. And then you have your custom client, whatever kind of wraparound you want to do, that's going to end up communicating with the business logic on the server side. But there's one kind of fundamental flaw in parts of the RMI architecture, because it's kind of assumed that without the stub, you can't talk to the business logic on the other side, because the stub contains a lot of secrets. But imagine you had the ability to create your own stub, to be able to just interact with any RMI service you felt free you wanted to do. Well, it is actually possible, because there's serious fundamental flaws in the skeleton layer. And this is going to allow us to create our own stub, and we can create our own client to talk to the business logic on the server. Now, just before we begin attacking an RMI service, there's a quick two kind of details you need to be aware of, which is the RMI Registry. And you run the RMI registry on the server. It's a separate process, and this is where you bind your objects to. And this is how other developers and the clients know how to communicate with your server. They need to know that there's an object sitting on a server side, and need to know how to make references to it, very much like any typical distributed computing technology. So the server registers their objects, and then the clients retrieve a name from the server to get a remote reference, and it can start talking to it, provided they have this stub. And by default, it runs on port 1099. So I mentioned earlier about the stub and the skeleton. These get generated by the RMI tool, and this is one of the tools which generates the the flawed code. So you generate the stub and the skeleton, and you're going to distribute this stub over to all your clients, and now your skeleton, with all the code flaws in, is going to sit on your server side, and you're going to build off this kind of a weak layer. So you can use, to set up your registry, you can use the RMI Registry command, which I'm sure many of you are familiar with when setting up your RMI service, or you can just do it at the API level. And one other very important detail about how RMI communicates is that it uses a 64-bit hash. So kind of with web services, it uses method names, and has particular details it needs to send over the server so it knows what you need to communicate. And with RMI, it uses a 64-bit hash. So you pass your 64-bit hash from the client. This is all detail that is generated for you and stored in the stub layer. And this will go over to the server side, and it'll be based on the hash and a couple of more details. It'll determine which method it needs to execute at the business logic layer. So this is a kind of critical detail, being able to map out the business logic and knowing how your client's going to communicate with your server. Now, the SHA hash is actually generated using a method name and method descriptor. So you can see I have an example there. Unfortunately, it's kind of fuzzy. But the idea is that the method descriptor is passed in, SHA-1 hash is generated, and there's no seed. So you can actually generate these hashes based on people's API documentation. So if I knew certain methods residing on your server, I can generate the hashes. I know your keys. And this is all about the hash weakness. The fact that you can pre-calculate hashes. If you get hold of someone's API documentation, you can start building these keys, and he's going to give you access to talk to the RMI service. And it's 64-bit, okay? You're not going to brute force a 64-bit range overnight. There's 18 trillion combinations. But actually, for doing more analysis on this, it's not actually 64-bit. Some have done a kind of funny implementation on the SHA hash, and they've shifted a few bits around. I don't know why. And the entropy is a lot lower. So I'm still doing the analysis on this, but already there's at least 2 trillion keys that are missing. So it's taking the attack vector down greatly. So if you're going to attack an RMI service, what do we need? We need to be able to communicate with the registry. So we need to know what are the bound object names. We need to know what's the stub name. As we've seen, you need a stub and a corresponding skeleton, and these names must match up, otherwise the stub and the skeleton won't communicate. And as I just spoke about with the 64-bit key, this is going to give you access to the service, so we need to retrieve this detail as well. Okay. And obviously you need to retrieve the method prototypes. You need to understand what...
Sorry about that.
Check.
That much better.
Okay. Cheers, guys. Okay.
Sorry, everybody. If you start from the beginning.
Okay, so I was talking about the method prototypes. So very much when you want to interact with a web service, you need to know what the function calls are. And we've got to determine its detail as well, because you've got the business logic layer, there's some functions hosted, but how do you know what to pass to it, what are the return types? So obviously this is a critical kind of piece of information to know how to talk to the business logic layer. And also, the tools only give you so much detail, but it's enough detail to code your own client, so you need to have a bit of a Java coding experience, and you can start knocking up your clients and really start attacking the RMI service. So today, I'm going to host an RMI service. I'm going to host 3 methods, so I'm going to show you the implementation of that. I'm also going to take a big chance, and I'm going to do a live presentation. There's no videos. So we're going to host this RMI service, and we're going to attack it. So, please bear with me if any kind of fat fingers or any silly mistakes I make. So we're going to work through this RMI assessment methodology, which I've put together. And this is how we kind of perform an assessment within Corsair. So first step, we need to know that the RMI service is there and what is the remote object name. So we're going to do a demonstration now. We're going to quickly set up the RMI server. So you can see, no, you can't see. But okay, so that says, we'll just, I'll pull it across a bit. Okay. Okay, so the command is start RMI registry. And as I talked about earlier, you need to create your registry. You can either do it using a process or at the API level. So we're going to start that process, and now it's just sitting there on port 1099, and you're going to register your objects into the registry. So it's not a particular interest now, it's just going to help us get our RMI service running. And we are now going to start our RMI service. So you execute your class. So people who are familiar with developing RMI services, you see that you actually just run Java with your business logic, which implements certain interfaces, and you've extended certain classes. But I'm not going to go into the detail of how you actually implement an RMI service. There's plenty of tutorials to do that. So it's going to have to do this. It doesn't all fit on the screen. Okay, so as I said, step 1 of the methodology is to retrieve the bound object names. I'm sorry about the kind of quality of the slides. I don't know what's happened. I think you can read that. So we're going to run the first tool in the suite, which I've developed. It's just called RMI Spy Bound Objects. Very kind of simple tool to set up, as a lot of the detail is there in the Java API, and it just takes 2 simple details, which is the IP address. So we're just going to run off localhost today. And it responds with the bound object name that I put in my RMI service called Owasp5024. So we're going to take a note of that, because that's our first detail that we needed on an attacker's shopping list. So the bound name is Owasp5024. So that was straightforward enough. Step 1 is very simple. Step 2, determining the stub name. So my skeleton is sitting there now, ready to take invocations on my RMI service, but we need the correct corresponding stub name in order to match the invocations. So we're now going to quickly retrieve the stub name. Again, it's a simple process with the tools. So this tool is just called RMI Spy Stub Name. And you're going to see, as we go through the steps, the next step requires a detail from the previous step. So the parameters which need passing in here are the IP address again of the service, the port number, and then a bound object name, which we retrieved in step 1. And that's going to now tell us what I need to call my stub name when I'm trying to build my custom kind of client side. As we saw in the architecture, there's several layers, and we're trying to implement that stub layer. We don't want the developer to pass it out. We found a RMI service we want to attack, so we need the correct stub name, and RMI Spy Stub Name is going to tell you what the server expects, what the corresponding stub should be for communication with the skeleton. Again, we'll store that in our shopping list. We don't need that. Okay. And we were here. Okay, so we've already completed step 1 and 2 of an RMI assessment. Now it becomes a little more complicated. We need to dig out method hashes. Method hashes are used for 1.2, and today we're going to dig out what's called an interface hash for 1.1, as the implementation changed slightly as Sun developed 1.1 and 1.2. So we're going to run a brute force attack against the server to determine the actual 64-bit key, which is going to allow us to invocate on the server. Now, when you're communicating from the client to the server, this key is constantly sent over, so it knows it knows that you're kind of an authorized client. But we're going to retrieve that, and this detail is actually stored in the lower layer of the RMI architecture. So I'm going to actually slightly cheat today, because if we just brute force a whole 64-bit range, you guys aren't going home for a long time. So we're going to run RMI spy method hash. And again, this takes a bit more detail that we retrieved from the earlier steps. And there's also a few slight code modifications we have to make for this tool. So the RMI spy method hash is going to attempt to make invocations on the server. Now I've retrieved the stub name, and I'm going to need this for the RMI spy method hash tool. And this is step 3. So this is a kind of template that I've written. You don't need to worry about too much about the implementation. You just need to make a quick code change based on the detail you've retrieved. The stub name we retrieved earlier in step 2 was called sample server stub. So we're just going to update the template just to fit in with the Java conventions. And then we have this kind of fake stub that I've implemented. And this is going to allow us to start communicating with the RMI service. Okay. So I've made a quick code change there to the class, just so it fits in with the correct stub name that the server expects. So we're going to recompile that now and use our... No, because I haven't renamed the stub. So you also need to rename the stub name to the detail that we retrieved in step 2, because obviously that's going to fit in with the Java conventions. Your class name and your file name must be the same. So we're going to recompile this now, and now we're ready to run RMI spy method hash. So we can see the details it takes. It's looking for where the actual RMI service is hosted, and the object name, which we retrieved in step 1. And then RMI spy method hash will take a hash as a final argument, and it's going to increment the hashes and try and brute force about what hash exists on the server side. And as I said, we're just looking at 1.1 today, so once we retrieved one 64-bit hash, we essentially can start taking control of the server. It's going to allow us to interact with the business logic layer. We can start kind of doing whatever we feel like. So we're going to start with, as I said, I'm going to kind of cheat. I know what the hash is because I developed the RMI service. And we're going to brute force, say, 400 keys. There you go. RMI spy method hash is now attempting all the hashes at the starting point that I gave it. We've tried 401 hashes, and it's now identified the correct hash on the server side as, well, whatever the number is. And again, we're going to keep tabs on what this interface hash is. I'm going to build up these details the attacker's shopping list. So we know the bound name, we know the stub name, and we now know the interface hash, which is probably one of the hardest details to retrieve, but I'm going to show you later on. There's going to be new additions to RMI Spy, and there's going to be many ways to help you retrieve this key. Okay, so we now have the key. I'm going to show you that as we've been running the RMI server, you can see that I actually had many kind of debug messages to go out on the RMI server. You're going to see them kind of happening when we start invocating. But you can see so far we've profiled a lot of details about the server, and there's not been kind of any messages, anything printed out. So even as a developer, if you kind of had some local messages to be displayed, you're not going to see any of them yet until an actual attacker has developed a successful client, and you're going to start seeing messages appearing as we're developing our own client. So this brings us on to determining the method prototypes. So we've got the first three details, but we need to actually know what's actually hosted on the server. The same concept as a web service. What's the method? What values does it take? What's the parameters? What's the return type? So we're going to use another tool in the suite. And this one is called, original name again, RMI Spy Method Prototype. And you guys can just about see that. Okay? And again, just same as the other tools. It takes an IP address for the service. It's looking for the bound object name, and also there's a new kind of detail we need to pass to this tool, which is going to kind of make more sense to you how the actual invocations of RMI works. You see that one of the arguments is a method number. Now when you host your methods on an RMI service, they start at kind of 0, and if you have, they go up sequentially. So your second method is 1, your second method's 2. So what's actually happening on the wire of an RMI service is that the client sends over the 64-bit key, and then it's going to send a corresponding method number as well. So the 64-bit key is always static. So if you want to execute method 1 on the server, you're going to pass in 0. Execute method 2, we're going to pass in 1. And we're going to use this to start profiling all the different methods that exist on the server. So logically, we're going to start at method 0. What's the first method that's actually bound on this Owasp object? And we're going to need to pass the interface hash in to begin a successful invocation. And I did just forget one small step. As we did in step 3, we need to have the correct stub name again for step 4. So we're just going to make a quick code change again, very straightforward. Just replace the stub name with the one that the server's expecting. Again, just make sure it fits in with the kind of Java compliancy, with the names it expects. So at this point, this is what you would actually expect it to be handed by a developer. This stub that I've created here, once we compile it, this would have been essentially the key that a developer or administrator, however you want to host it, this would have been the key to how you would have communicated with the RMI service. But we've actually started developing our own now. So we've compiled our own stub, and at which point we can start now invocating methods on the server. So we're going to profile method 0, as I said earlier, and we're going to pass in the key which we retrieved in step 3. And now you're going to start seeing how we're going to profile the method prototypes. Okay, so what's actually RMI Spy method prototype telling us? Unfortunately, you can't read a lot of this output, so I'll kind of explain it in a bit more detail. I think you can see that. So RMI Spy method prototypes is telling, yeah, there is an Owasp object on the service, and it's attempted to invoke method 0, and what it's actually done is passed a vector object into it, which has fired an object over saying, hey, what's your first parameter? Fired an object, and the server's actually responded saying, no, actually, I want an integer for my first method. So we've just kind of started profiling now. So what we're going to do is update RMI Spy method prototype, and you can see here where I've just fired over the vector. So we're going to fire an integer. I'm going to see how the response changes. So you've got to do a slight code modification at the state RMI Spy is in. So you quickly recompile, and again, just run it. And now it's accepted an integer. We knew that the RMI service was expecting an integer because of the first run we did on the tool. But now it looks like RMI Spy method prototype has crashed. I assure you it hasn't. What is actually happening is that the server is still listening on the socket. It's accepted the first object, but it's saying, well, I was expecting more parameters. So the server's just sitting there now saying, hey, where's the second object? So we can do a quick update to RMI Spy method prototype, and again, we'll just fire over a vector, whichever object you feel like. Again, a quick compilation. And now we're going to attempt to profile method 0 again, firing over the integer and a vector. And now the output's changed again. It's said that, hey, yeah, I've accepted the first argument from the integer. For the second argument, you passed me a vector, but I was actually expecting another integer as a second argument to my method. So again, it becomes a kind of a slightly tedious process at the moment. So again, we're just going to do the code update, and it's the same process. We're going to recompile. At this point, I'm going to show you what's actually happening with the server. So the server's still waiting there. And we're going to run. And now you see what's happened. RMI spy method prototype has now determined the method 0 on the server. It knew that it wanted 2 integers. We passed the 2 integers in, and the server responded, actually sending us back a long object. An RMI spy method prototype will tell you the return type of however the server responds, whether it's a custom object, whether it's an object that exists in a Java API, and it's also going to tell you the value stored in the object. So we passed in 2 integers with value 10, and the server responded with a long object with value 20. We can actually see there's been a debug message off the server, which I implemented at the kind of server level. That was me as a developer implementing the business logic layer, and I was saying whenever this method's executed, I'm going to print a debug statement and tell me what values were passed in. It's kind of typical developer techniques, is kind of debugging your own software. But we can see that there's been a successful invocation. So based on all that detail, for the method prototypes, we now know that the server is actually hosting a method that has a return type of long, and we're going to call it method 0. There are ways to actually retrieve the method name, but I'm not going to go over that today. And we know that the method 0 on the server takes 2 integers. So we're going to profile another method quickly, just to kind of get into the idea of what's actually happening. So I'm going to rewind the attack code slightly. We're currently passing over 2 integers. I'm just going to go back to firing over my fateful vector. I will do a quick recompile again. And we are going to now start profiling method 1. We know all about method 0. And at that point, we could actually start developing our client and just start concentrating on the first method of the RMI service. And again, similar to the profile of attempting to retrieve the details about method 0, we fired in our object. This time, the RMI service for method 1 is saying, no, I was expecting a big decimal as my first parameter. So we're going to pass it our big decimal. You can kind of see how we're dealing with more kind of complex objects. RMI spy method prototype doesn't mind about that. For those of you familiar in Java, everything's an object, so we can kind of talk to all this stuff. So I'm going to fire at the big decimal. I'm going to put a value in as well. Just 20, doesn't matter. The idea is you just fire over an object. And again, the server is waiting. It said, yeah, I've accepted your big decimal, but I still want more data. So we'll quickly finish determining the method prototype. Again, we're talking to method 1. And now we can see that we fired in a vector, and it's saying, no, my second argument for my method, for method 1 on the server, is a string. So we're just going to give it a quick string. We'll send it over a nice message. And again, it's saying, yeah, I've accepted those 2 arguments, but I was still accepting a third parameter. So you can see how it's kind of becoming tedious, but I'm going to talk to you about the development of RMI Spy and how you luckily won't have to do any of this. And there we go. It happened that I just fired off a vector as a third object, and that is what the server was expecting. So method 1 on the server, it was actually expecting a big decimal, a string, a vector, and it responded saying, hey, here's your big decimal object back, I've done all my business logic, and here's value 10. So we've now profiled the second method on the server. Again, the return type was big decimal. I'm just going to call it method 1, and it takes a big decimal, a string, and a vector. And that's a lot of detail from how far we've come. Well, we only knew that there was an RMI service being hosted, and look how much information we've now retrieved about this RMI service. We've actually got all the secrets and actually understand what's kind of going on at the business logic. We know a developer has implemented 2 methods, and we can start invocating these and do exactly what we want to them, pass whatever data, start analyzing the return type, do the methods, throw back certain exceptions if we start to fuzz it or give it specific Java payloads, because we can start attacking the actual developer now. We know developers make mistakes, security is difficult. So at the business logic layer now, we can start attacking this. We now have the details of the business logic layer, and we can start attacking the developer's implementation. We've attacked Sun's implementation lower down, the skeleton layer, and now we've attacked the business logic layer. We've worked our way through the RMI architecture. Again, you can see actually the last method I invocated as we were kind of profiling it. We passed in 20, the big decimal. We passed in a string saying hello Owasp, and we passed in a vector, and you can see how the vector's actually dumped to the console. And at this point, you kind of realize that with your Java RMI service, if you're not careful about the logging and the detail of actually looking who's invocating your RMI service, we actually see there was nothing, no detail was even given to us until I successfully determined your method prototypes. And then because it's just the debugging information that the developers put in, it's actually come to the console. So the chances are you haven't even noticed that an attacker's just profiled your whole server, and he starts actually developing his own customized client. And there we go, we've worked through step 1, 2, 3, and 4, and look at the amount of information we retrieved from 0-day knowledge. And then step 5 is the ability to actually create your own stub. This is where you become creative as a developer, as an attacker. This is where you actually say, well, okay, I know which methods they've implemented. What data am I going to fire over to try and start really pinpointing what the business logic layer is about? And you can obviously look at stack traces and try and rely on the common coding mistakes that occur at business logic layer, and we can determine a lot more detail. As I said, you can retrieve method names, you can retrieve implementations. So for example, you're trying to force stack traces being thrown back to you as an attacker from the server. For example, imagine trying to invocate a number format exception or division by 0 exception. And when you get a stack trace back in Java, for those of you who actually do any development, realize how much detail is given back in a stack trace. You can go through and look how many lines of code have kind of been implemented, look at certain classes, implementation, where the control flow is. So you've kind of done the hard work now. You've actually assessed the whole RMI service. Now it's time to get kind of really creative and develop your own client. 5 minutes, okay. So why is RMI insecure? How has it been possible to retrieve all this implementation, all these kind of details about an RMI service? Well, it's because of the skeleton, this layer that resides on the server side, and you're actually building your business logic layer on top of this flawed skeleton. You kind of really need to understand about the Owasp top 10. You know, the Owasp top 10 doesn't just apply to web applications. Some of the features in the Owasp top 10 do apply to applications in general. And the skeleton leaks vast amounts of detail. And if the developer follows any of those kind of same coding mistakes, you're going to be able to retrieve so much more detail. And it's also the whole concept of RMI, this idea that, hey, there's a client, there's an object, and there's your magic, it talks. This false sense of security causes big problems because the developer doesn't know what happens. He doesn't need to check the lower layers. He's only concerned with his business object. So it kind of really does create this false sense of security that Sun have taken care of everything you're developing on top of their layers, but the layers are flawed. And it's also with the key and the insufficient key space. As I said, it's a 64-bit signed key, but it's not actually a 64-bit key space. So it does not have 18 trillion combinations. And as we've seen, we actually brute forced the key, and I kind of cheated. But it doesn't take long to actually go through several thousand keys a second, 10, 20,000 keys, especially in today's computing resources. And as during the demonstration, the chances are you won't know an attacker's actually profiled your service unless you actually go about doing certain security features that I'm going to quickly go over. So how do you secure an RMI service? Well, there's a couple of recommendations I have for you. Look at the skeleton code, look at what's actually happening at your lower layers. It's not magic. If you understand Java, if you can read Java, quickly understand about the skeleton and the stub and the relationship, and modify your method hashes. The key space is insufficient. Make it unfeasible for an attacker to actually retrieve the key. You wouldn't actually have a session ID on a web application that was 64-bit, so why have a static 64-bit for an RMI service? And again, make sure your authentication and authorization is implemented correctly, just as you would with your web applications. So something like the Java authentication and authorization service, it's an API that's going to help you implement your authentication and authorization mechanisms correctly. Because don't assume that just because you're hosting services, that the corresponding stub you give out is just what the clients can see. We can see that if you develop just a couple of methods on your server and you gave a client out that says, hey, you just have access to one method, it would be trivial for us to assume the rest of the functionality and determine it and start developing our client to get all the functionality on the server. And think about your RMI architecture. Don't just expose an object directly. This is what you'll see on a lot of the tutorials. In fact, I've seen it for every implementation I've assessed myself. The object's just hosted, very much like you'll find in WebSphere and JBoss. The Java Remote Management Console is an RMI service, and this functionality is just it's actually released just directly. Think about using a proxy. Don't just allow people to retrieve your reference names for your objects. Your client should have to go through a proxy. They need to authenticate. Then you start passing the details and start checking out what your clients are doing. And again, don't just think about this it's secure because it's magic. Look at the layers, think what's going on, even have a look at the packet traces. I spent a lot of time going over the packet traces to see what was actually happening on Sun's stream-based connection. So start thinking about it in a bit more detail, dig down in this RMI architecture, don't just assume that everything's going to be okay. And enable logging. As I shown during the demonstration of the attack, there wasn't actually any evidence an attack was taking place, but I'm going to quickly show you what happens if we implement some logging on an RMI service. And unfortunately, not many people do this when they're hosting their RMI service. I'm just going to take down the RMI service. I'm going to start it back up. But this time I'm going to enable logging, which is actually a Java environment variable for RMI services. Okay. So the service is running, and we can already see there's some kind of details. It's going to give us fine debug details. And I'm going to quickly run across the brute force attack, and you're going to see now how things change at the server. So anyone looking at the log files, anyone managing the RMI service will automatically see that an attack is happening. So let's run the brute force attack again. And look at all this detail that's actually happening at the RMI service. See stack traces. It automatically tells you someone is running an attack. They're trying to profile the RMI service. So with logging enabled, you're going to have a greater chance of detecting someone is profiling your RMI service before they've actually developed their client and understood your functionality. So you've seen that RMI spy is actually kind of tedious, requires some code changes, you need to understand Java, you need to recompile some stuff on the fly. But I'm going to make it fully automated. I'm going to take all five steps of the methodology. It's going to be a single click and run. For those people who love GUI, sure, I'll put a button on it. There's going to be automated interfaces, stub creations. You're going to have packet sniffers. I'm implementing this in Java at the moment. It's going to be reading the packets off the wire. It's going to be looking for the 64-bit key secret. It's going to be pulling off objects. It's going to be looking at what the other clients are, what the implication is actually happening, the conversation between the client and the server, what objects are they sending across, what values are they sending, what's the response from the server. And it's going to pull these objects off the wire, and it's also can modify them on the fly. So if a client sends strings through or hash tables or vectors, the RMI spy is going to look for these details, going to modify them on the fly, and it's going to replace some of the client conversation, this legitimate client conversation. It's going to run a lot of attacks. Obviously, you need to set up your man-in-the-middle attack. However you want to do that is up to you. There's going to be a huge code tidy. There's going to be a big rewrite. And as I mentioned earlier about the hashes, you can actually profile people's key on the server, because all you need is access to their API documentation, or you can even talk to a developer, ask him about some of the methods he's implemented. And if you know his method names and the objects that he's passing as parameters, we can work out his hash. So even through social engineering or available API documentation, we'll be able to generate the hash ourselves, and that's going to save us a big legwork for the kind of brute force attack. The stub that's going to be automatically created is going to do fuzzing for you. It's going to have exception handlers in. It's going to understand what's happening at the business logic layer. It's going to have specific Java payloads in. If you want to look at some specific Java payloads, I recommend checking out the Java Owasp gotchas page, which I've been writing. And thank you for some of you who have been helping implement some of those features there. So it's going to be attacking the Java API and making a lot of the business logic layer fall over, a lot of the features that developers don't know about that you can take advantage on. And I'm going to multi-thread the hash attack. I'm actually going to develop it either in C++ or assembly. I'm actually going to mess around with the sockets. I'm going to do the packets. I'm going to make it very, very fast. I'm not going to use Java to help me do this. I don't want to write objects onto the wire. I need to make it very fast. I'm going to construct my own packet, deal with the TCP IP connections. I'm going to really speed up the hash attack. So, as promised, we looked at the RMI architecture. We saw what makes an RMI service. We saw what makes RMI tick. We looked at where the fundamental flaws lie within Sun's RMI implementation. We looked at why RMI is insecure. If you actually read some of the code generated by the RMI C tool when you're creating your stub and your skeleton, you're actually going to see there's a comment in there by Sun saying do not edit. But I kind of beg to differ, and I'm sure you guys do now. You need to edit it to make your RMI service secure, secure your lower layers. And we looked at RMI Spy. This is the only tool which is being developed publicly to assess RMI services. I'll be making it available in the coming weeks. I'll probably open it as a Owasp project, so it'd be great to have any kind of Java developers, any people who are interested in RMI to help contribute to this. And we looked at how to secure RMI. We looked at how to enable logging, things you need to think about the authentication, the authorization, implementing a proxy, and changing the skeleton. Well, thank you very much for listening. Hope a lot of you haven't covered RMI before, have kind of learned a lot more about it, and you're going to be a bit more wary about implementing your RMI services in the future. So is there any questions?
Well, how long does it take you to break a hash, and what information do you have that the functions you input to the hash function are weak? You made that claim that that's permanent.
Sorry?
Sorry, you're making a claim that the generation of the hash key is weak or something.
Yes.
I mean, what information do you have? I mean, is it a deterministic algorithm? Do you know it?
I kind of put a comment up on the slide saying I'm still doing some more analysis on that, but the message digest which is used, it's not actually seems to be implemented correctly. Sun are moving around some of the bits, so they've generated SHA hash, and they start kind of mixing some of the data around. So it's not clear what they're actually doing. It's going to require a lot more analysis and gathering some more kind of static ID to see what's happening. And give you an idea of where's the best place to actually attack. As I said, there's actually 2 trillion keys missing at the Sun's implementation. So what you'd expect at least 18 trillion keys from a 64-bit value, but it's already down to 16 trillion. I know that's still a large number, but it's through further analysis, it looks like actually might be more of a 32 to 48-bit key. In terms of the key space.
But even if I take if I take things that are functionally near and hash them, they're not going to be closed after they're hashed. So, I think you either have to know the algorithm generates the input to the hash to get it.
Yeah, you have to know the API documentation if you wanted to generate your own hash. I would ask you, I'd say, what's one of your, as a developer, I'd say, hey, what's your API documentation? Have you got any copies of your API documentation? Based off your API documentation, I'll just pass the method name in, and then I know what your hash is for your methods.
Can we take this question offline? We're running short on time. One or two more questions? Put your hands up.
Just a very basic question. The Android